In this video, we will continue our look at alkane conformations, looking at some higher alkanes. So let's begin with butane. This is a 4-carbon alkane, and because it is named butane, we know that those carbons are all in a chain using the IUPAC name. If we were to cite down the C2-C3 bond, so let's imagine that we are looking down this way. So on our front carbon, we're connected to a hydrogen, and a methyl group, and this would be our back carbon connected to a hydrogen, and a methyl group. Just like ethane, butane can take on different conformations. We can have eclipse conformations, and we can have staggered conformations, and we have an infinite number in between. We have rotation around all the CH bonds, but that doesn't lead to any difference in the molecule. We have rotation around these bonds, but for now, we're just focusing on rotation around this bond. So on this slide, let's just focus on the staggered conformations. And I'm going to draw 3 frameworks for Newman projections. So if we have 1, 2, 3. So on our back carbon, we can have a bond up, down to the left, down to the right. So let's keep that the same. I drew that in a little bit too far. And then our front carbon, now let's put a bond down, up right, up left, bond down, up right, up left, bond down, up right, up left. Notice up here, the front carbon has a bond straight up, but in these, I drew my front carbon with a bond straight down. We can draw it this way, we can draw it this way. However we decide to put our first set of bonds on the front carbon, for example, we just have to make sure that the back bonds are consistent with whether we're trying to draw staggered or eclipsed or something in between. I just want these 3 to be the same so that we can consider the difference between the conformations of butane. Once again, we are looking down the C2-C3 bond. So let's imagine that on our front carbon, here is the CH3 group, and then the hydrogen and the hydrogen. And let's keep that the same. So methyl, hydrogen, hydrogen, methyl, hydrogen, hydrogen. Now on the back carbon, once again, we have hydrogen, hydrogen, and methyl. So we could have hydrogen, hydrogen, methyl. But then we could imagine if the front stays still, but let's rotate, think of this as a little steering wheel, and let's rotate around the back carbon. Then we can rotate to put our methyl here, hydrogen here, hydrogen here. Keep turning that red steering wheel until we get the methyl here, hydrogen here, and hydrogen here. All right, so all of these conformations are staggered conformations because this front bond bisects the 2 behind. But notice we have a difference that these are not equal to each other. Here we have our methyl groups kind of near each other. Here we have our methyl groups kind of near each other. But here our methyl groups are completely across from each other. So this one is called a gauche conformation. This is also gauche. And then this one is anti. And here we introduce our second type of steric strain, and this is called van der Waals strain. Which we can think of as steric hindrance. In other words, if the atoms or groups are too close to each other. So here, if we consider our methyl groups, off of each carbon, we have those 3 hydrogens. Overall, it's a tetrahedral arrangement, and it just puts those hydrogens a little bit closer to each other than what they prefer. So there is a van der Waals radius of every atom, and if another atom gets within that van der Waals radius, then there's a little bit of van der Waals strain. So when you have methyl groups gauche to each other, you have some van der Waals strain. So here we have van der Waals strain. Here we have van der Waals strain. Here we have no van der Waals strain. So all of these have no torsional strain because they're staggered. These have some van der Waals strain. This does not. So out of these three staggered conformations, this one is going to be the most stable because it has no strain. These are going to be a little bit higher in energy because they do have some van der Waals strain. Next, let's continue to look at butane. We are continuing to cite down the C2-C3 bond. So imagine that we are looking this way. And now let's focus on the eclipsed conformations. So I'm going to draw my back carbons. So this would be C3, and I'm going to have bond, 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 bond. And so that is this carbon. And then if I have my front carbon, well, these are eclipsed. So this front carbon has a bond down, a bond up and to the right. And so they're all pretty much right on top of each other. So I want to get them really close on top of each other, but I still want you to be able to see both of them. Okay, let's do the same thing and keep our front carbon still. So let's have the CH3, H, H, CH3, H, H, CH3, H, H. Now for our back carbon, let's say we have the CH3 here, H, H. Now keep the front carbon still and turn the steering wheel so that the back carbon turns this way, and that will put the methyl group here, hydrogen, hydrogen. Keep turning, and that puts the methyl group here, hydrogen and hydrogen. So because these three are eclipsed conformations, we know that they already have torsional strain. In addition, this methyl group compared to this hydrogen, we're going to have some van der Waals strain. Here we also have van der Waals strain, some van der Waals strain, some van der Waals strain. Here, where our methyl groups are eclipsed on each other, we're going to have a ton of van der Waals strain. Now, there isn't a specific name for these. All three of these are eclipsed. I tend to call these eclipsed, eclipsed, and fully eclipsed. So when our biggest groups are eclipsed on each other, this is going to be the worst situation because it has the same torsional strain as the others, but it has the maximum van der Waals strain. So let's pull all that information together, and here we have an energy diagram. Here's our potential energy increasing in this direction and our torsional angle. And here we're starting out with our methyl groups up top, and they are eclipsed, and this is high energy because we have torsional strain and van der Waals strain. As we take the front carbon and turn it so that we are rotating around the C2-C3 bond, then we are going to decrease the torsional strain, decrease the van der Waals strain until we get to the first gauche conformation. And this is lower energy, more stable than what we started with. If we continue rotating, we're going to get to the next eclipsed conformation, but here we have the front hydrogen eclipsing with the back methyl group, the front methyl group eclipsing with the back hydrogen. So it has a lot of torsional strain and it has some van der Waals strain, not as much as what we have here. So it's at the top of a hill, but not as big of a hill as this one. If we continue to rotate, now we get to our anti-conformation. So the front carbon has a methyl group straight down, the back carbon has a methyl group straight up. There is no torsional strain and there is no van der Waals strain. So this is at the lowest energy, even lower energy than the other valleys. Keep rotating along here, and we get up to the next eclipse conformation where it's partially eclipsed, hydrogen on methyl, methyl on hydrogen, and that's the top of a hill. Continue to rotate and we get to another valley, but because we have some van der Waals strain, this is another gauche conformation, so this valley is not the deepest valley. And then continue to rotate and we get back up to our completely eclipsed conformation with the maximum torsional strain and the maximum van der Waals strain, making this one the most unstable overall. Now here, going from the most stable to the least stable, we have an energy difference of 25 kilojoules per mole. So it's a little more than twice the barrier that we saw in ethane, but still it's not much of a barrier, and we still have rotation around this bond. So these can interconvert still very rapidly. Finally, let's think about conformations of higher alkanes. So can we carry out a conformational analysis of pentane and hexane and heptane? Yes, of course we can. We can do the same approach. We would need to define which bond we're looking at. So if we're looking at this one, for example, then our front carbon is connected to hydrogen-hydrogen methyl, and our back carbon is connected to hydrogen-hydrogen ethyl. On this one, we could look at the conformation along here, or we could look at the conformation along this bond, right? So we can do the same thing, we just might have to add a little more detail to all of it. But we can do conformational analysis on bigger alkanes. What if we had a branched alkane? What if we had something like this? We can still do conformational analysis if we were looking at this bond and we're looking this way, then our front carbon is connected to a methyl, and a hydrogen. Our back carbon is connected to an ethyl group and a hydrogen and a hydrogen. So we can still draw Newman projections. We're going to have different things at the bonds, but we can still do conformational analysis. One of the things that I want you to notice, though, if you remember, the anti-conformation is always going to be the most stable because there is no torsional strain and no van der Waals strain. Well, if we are looking at pentane and we're looking along this bond, then that means that this is down and this is up, so that we have the anti-conformation. So this shorthand structure, it shows us connectivity. It can help us think about the shape in terms of the tetrahedral arrangement of the carbons, and then we just have to mentally fill in the tetrahedral arrangement of the hydrogens. But now it can also remind us of the conformation where the preference would be anti-conformation.